asking, it is required to find the incremental resistance of each of the diode connector resistors shown in figure P8.21. Assume that the DC bias current I is equal to 0.1 milliampere for Mosfet. Let mu and Cx is equal to 200 microampere per voltage square and W over L is equal to 10. Neglect RO for both devices. Okay, here I'm just going to do the A part, that is containing Mosfet, and the B part with the BJT I will do in my next videos. Okay, so let's look at the A part here. And here we are, the question is asking us to find out the resistance, and the resistance we have is input resistance. Now in order to better illustrate this one, we can draw the small signal equivalent model, and for the small signal equivalent model for the MOSFET look like this. We will have a ground on top like this, and then this is drain, and in the bottom we will have a source. Okay, this is ground, this is drain, and this is source, and between ground and source there will be a VGS voltage. VGS is nothing but VG minus VS, that is located right here. In small signal equivalent model, that will be right here. And this is an NMOS, that's why we have GDS like this. If it's a PMOS, this will be flipped. Okay, this is VGS, and from drain to source there will be a current flow, that is ID current. And in small signal model, ID is, we can express ID as GMVDS. So this is also equal to GMVDS right here. Okay, and if you see, this MOSFET is diode connected. There's a connection between the drain and the gate, so it means there will be no gap like this. This will be connected fully. And also they said neglect RO both devices, so it means there's no the output resistance is not there. The output resistance usually between drain and the source, if it's there, it will be connected like this. Okay, but there's no output resistance. So the resistance we have to find is the input resistance, that is over here. Okay, now to find out the input resistance, we can use the Ohm's law. Ohm's law says V is equal to I times R. Therefore, R is equal to V divided by I. In this case, the V is VGS, and the current flowing through this is GMVDS. GMVGS, okay, not VDS. GMVGS. Okay, this is just Ohm's law, like V is equal to I times R. R is equal to V divided by I. V in our case is VGS, and the current in our case is the current source that we have right here, that is GMVGS. So we put it right here, and here VGS cancel, so Rin comes out to be 1 over GM. But GM is not provided in the question, so we have to figure out what GM is in order to solve for Rin. There's two ways you can go about it. Like, one way is you can use the current equation and solve the unknown variable, or you can directly use the GM equation. Let's try using the GM equation directly and let's see what is missing. So if you use GM equation, the GM transconductance is given by mu and Cox W over L times V over drive. And if you notice, we have mu and Cox readily available. We have the W over L also provided in the question, but we don't have the V over drive. But if you notice, there's a current provided, and since we have the current, you can either use this equation and solve for V over V as well. You can go ahead and use this equation. I is equal to half time mu and Cox W over L over times V over drive square, and solve for V over V, because since we have the current, V over V is the only unknown variable, and you can solve it using this equation. Then you plug that V over V here and solve for the transconductance. Or you can use another equation, that is V over V also equivalent to 2ID over GM. 2ID over GM. So if you do that, then this equation becomes just one unknown variable, because ID is already there. provided in the question. And gm, we can bring it and multiply on the other side, so it's only one unknown variable, so we can solve it. So we do that, then this one become gm mu n cox w over l. Instead of v over drive, I put 2 id over gm, and gm I bring it to the front, bring to the other side of the equation, so that's going to be gm square, and 2 you can bring to the front, and then mu n cox w over l over w over l times id. Now plug in all the values. 2 times mu n cox is 200 microampere per voltage square, so 200 micro right here, and then w over l is provided to us, that is 10, multiply that one here, and then id current is provided to us, that is 0.1 milliampere, so 0.1 milli right here, and that is equal to gm square. And if you simplify this one, gm square comes out to be 0.4 micro. 2 times 200, 400 micro, 10 times 0.1, that's 1. So let me double check. 2 times 200 is 400, 10 times 0.1 is 10 times 0.1 is 1, and this becoming 400 micro, that is equivalent 400 micro, and also there's a milli. 400 is equal to 400 milli is equal to 0.4, so 0.4 micro. Okay, and if gm square is 0.54 micro, then gm is square root of 0.4 micro. Then if you solve for this one, that one becomes 0.633 millisiemens. Okay, now we have the trans conductance available, so we can go ahead and plug it in this equation and solve for the Rin. Rin is therefore 1 over gm, and gm is the one we just calculated, that is 1 over 0.633 milli, and that is equivalent to 1.58 kilo ohm resistance, and that's our input resistance. And that's it for this video. I hope you guys found it helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.